Welcome to Prediction and Calibration, Part 3 of the Practical Decision Making course offered by the Guild of the Rose. Visit guildoftherose.org for more details. How heavy is the heaviest blue whale? What is the GDP of Chile? What time is sunrise tomorrow morning? Now you might say, I don't know, and anyway, who cares? Well, in fact, practicing with trivial questions like these is a great way to improve your epistemic rationality. If you can build a set of skills that allow you to come up with answers to questions like these with well-calibrated confidence intervals, then you can use those skills to answer harder and more important questions like, what are the chances of my company's product succeeding in the market? What is most likely wrong with my car? Would I be better off working at a different company? Or when will AGI happen? In the book Super Forecasting, The Art and Science of Prediction by Phil Tetlock, a series of tools are introduced to improve your ability to address questions when you are not sure about the answer. Tetlock's entire career has been dedicated to improving the art and science of human judgment and prediction. Tetlock shows through a systematic study of a vast number of predictions made by a wide variety of people across a huge swath of topics that when it comes to making well-calibrated predictions, practice is more important than intelligence. In fact, practice can even be more important than having more information about the problem. More talented forecasters working with only publicly available information often outperformed professional intelligence analysts with access to classified information. So, it's hard to overemphasize how important practice is. Being well calibrated is synonymous with having strong epistemic rationality. What does well calibrated mean technically? Calibration refers to your confidence level being in line with your error rate. If you say, I'm about 70% sure that it's going to rain today, then you're expressing a 70% confidence level in that prediction. If you make a variety of predictions at the 70% confidence level, then you should be wrong 30% of the time. But if every time you predict 70% odds, and that set of events actually happens 90% of the time, then you're underconfident. If you predict 70% odds, and the event only happens 50% of the time, then you're overconfident. The goal is to be precisely confident. When you say something is 70% likely to happen, then it should happen 70% of the time. The process is one of learning to turn your sophisticated mental models and your gut feelings into a single accurate and useful number. A short sidebar. Another reason that we should learn to think in terms of numerical probabilities, to learn to turn what our gut and brain are telling us into a number like 70%, is that we can then share that number with other people and thereby communicate more effectively. You might think it's good enough to tell somebody that you're reasonably sure that you didn't leave the stove on, rather than saying you think the likelihood is 90%. But there's in fact no generally agreed upon definition for words like reasonably certain, probable, certain, and likely. In a survey, respondents gave definitions for reasonably certain that varied between 35% and 95%. Even proved, which I would think of as synonymous for almost undoubted certainty, means 65% likely to some people, apparently. If somebody told you that they had proved something, would you assume they meant that thing was only 65% likely to be true? Thus, use numbers, not vague phrases, to communicate probability. Let's return to our task of coming up with well-calibrated estimates and try to apply these ideas to the blue whale question we mentioned a moment ago. The question was, how heavy is the heaviest blue whale? The following was my actual thought process as I went through the process of answering this question. The aim here is not necessarily to show a correct, perfect way to go about making a prediction, but instead, I illustrated the basic principles. The first order of business in all prediction tasks is to clarify the exact meaning of the question and what qualifies as an answer. For the sake of simplicity, let's state that whatever weight that Wikipedia provides as largest or heaviest for blue whales will be accepted as the valid answer. Feel free to pause the video and go make your own estimate of the weight of the heaviest blue whale, and then return to see my approach. Next, I'm going to put forth a gut-based estimate and say that I think the answer probably falls between 25 and 100 tons, or 50,000 and 200,000 pounds, with about 80% confidence. In other words, about 20% of the time that I make a prediction with a similar level of confidence, I should expect to be wrong. I tend to lay down an initial off-the-cuff estimate before diving in to make a more precise guess using better tools. Next, I'm going to make a separate and independent estimate based on an analogy to a similar animal using my favorite website, getguesstimate.com, to help keep track of my probability distributions. Part of your homework for this week is to make an account on getguesstimate.com, so now would be a good time to do that, and you can follow along if you wish. I would guess that healthy adult blue whales are probably no longer than 120 feet and no smaller than 50 feet. That doesn't help much in and of itself, but it's a starting point. Here, I am going to employ a technique of analogy in comparison to a thing that I feel more confident about. I think that a bottlenose dolphin probably weighs between 250 and 400 pounds and is about 6 to 8 feet long. I base this purely on having seen them a few times and knowing roughly how heavy similar-sized animals are. I am at least much more confident about the weight of dolphins than I am about blue whales. I have, in other words, picked something that I am familiar with and understand moderately well to make inferences about something I am very uncertain about. If we simply scale up the biology of a bottlenose dolphin to be the size of a blue whale, you would expect the giant dolphin to have about 2,800 times as much mass, according to my calculation. This is because of the fact that the animal's volume scales with the square of its radius times its length, which is more or less a cubic relationship. But whales are thinner than dolphins in profile, perhaps 40 to 60% as wide as dolphins relative to their length. So I impose a factor which reduces the mass by this factor too. If we multiply these distributions together, guesstimate suggests that based on these assumptions, we should assign a median expectation of about 390,000 pounds, meaning we'd expect there's a 50% chance it's lower than that and a 50% chance that it's higher than that. In order to give ourselves a scoreable prediction, a prediction that can be judged right or wrong, we say that we are 50% confident that it's higher than 390,000 pounds. We finally look up the answer and find that the largest blue whale is 199 tons or about 400,000 pounds. Turns out that our median guess was pretty dang close. If we make a whole bunch of similarly accurate predictions, then we might be right 50% of the time and wrong 50% of the time, which means we are very well calibrated at the 50% point. In other words, we'd be really good at guessing the median value. If we're wrong half the time on predictions with a similar confidence level, we still win because we're well calibrated. And being well calibrated is the goal here. But we need to hold off before we give ourselves credit for being well calibrated. You may have wondered why I chose to use probability distributions rather than point estimates, and this is why. Distributions allow us to inspect the implications of our uncertainty and to interrogate our own understanding after we have checked our answer. The guesstimate model suggests that, based on our assumptions, we believe that there was a 20% chance that the animal would be bigger than 600,000 pounds, and similarly, a 20% chance that it would be less than 243,000 pounds. If the original question had been, what are the odds that the largest blue whale weighs more than 600,000 pounds, the model would have driven you to answer 20%, which seems very high now that you know the correct answer is only 2/3 of that. If you made a number of similar predictions about animal sizes using similar assumptions, does it seem reasonable that you would be wrong only 20% of the time? So we need to care both about the median value and the shape of the probability distribution, meaning we need to think harder about the minima and maxima of our estimates, not just our final median result. One thing that we could do to sharpen up not just the accuracy of our median estimate, but also the robustness of our distribution, is to make several estimates based on several different methodologies and average them together. You can then weight the averaging of these various distinct answers by your level of confidence in each approach. For example, if we decided to weight in our initial guess that the whale was unlikely to weigh more than 200,000 pounds, we would actually make our estimate worse. But we know that was a low-quality off-the-cuff guess, so we implicitly didn't give it very much weight. Or maybe you just happen to remember some other fact, such as a blue whale can weigh as much as 15 school buses. Then you can try to figure out how much a school bus might weigh. Or even just look up how much a school bus weighs if it's actually important. Another nice thing about building models such as this one is that we can check the validity of our assumptions in detail. For example, it turns out the largest measured blue whale was about 108 feet long, placing its length higher than our median guess, but still falling within our range. On the other hand, We were badly wrong about how big bottlenose dolphins are. In fact, they can grow up to 12 feet. If we had thought harder about the high and low end of our ranges, our ultimate guess might have been better calibrated. But, of course, this was only one prediction. We can't really say whether we were well calibrated from one prediction. We can only say whether we were right or wrong this time. Thus, you need to collect a fairly large number of predictions across a wide variety of topics to learn your own calibration accuracy. This is why we should keep track of our predictions in Metaculus. By the way, you can make a private prediction in Metaculus, or you can use a separate tool like predictionbook.com. Final note. Remember, our aim is to master practical decision making. In your day-to-day life, estimating the true weight of a blue whale is not likely to be important. If it comes up in conversation, you can probably just go with your off-the-cuff guess. And furthermore, if it turns out to be important, you could and should just look it up. A sophisticated forecasting procedure is only called for if the question is both important and uncertain. Thus, we practice our skills on these simpler, safer problems with known answers so that they're sharp when the harder problems crop up. This week, continue making one prediction a day on Metaculus and practice using getguesstimate.com or some other similar tool to help with your predictions. Before your cohort session, make an independent guess at the weight of the largest recorded elephant and bring that guess to the course session. If you're interested in taking the course, visit guildoftherose.org for more details or patreon.com/guildoftherose to join the guild. Click the link in the sidebar to view the playlist of videos for practical decision making.